teaching stuff because the multivariate derivation is so much more useful, and I think it's simpler. But it's only simpler if you're happy with matrix quadratic forms, because the trick we're going to have to do now is exactly the same, but for matrix quadratic forms. Okay, so I know that you won't have seen linear algebra all the time. So I've set aside quite an amount of time for doing this, and what I suspect will happen is I'll finish slightly early, and then I want to maybe go into Octave and start sampling from these things, because I'm going to introduce basis functions as well, which allow you to do nonlinear regression. I should point out that, sometimes, it isn't quite true, but sometimes I joke that this type of derivation is all I do in my research career, just with different structures of model and different types of conditional independence assumption, and you can get some really powerful things out of it. So knowing this stuff is kind of useful. So the multivariate regression likelihood was different. So instead of mx plus c, we get rid of the c because we can always say, well, we'll have an additional x which is set to 1. And we'll extend that idea when we look at basis functions a bit. So the idea is that we've got this vectorial form for w. So our parameters are now in the form of a vector, and on Tuesday we looked at optimizing this likelihood with respect to that vector, and we needed a little bit of matrix calculus to do that. Not very complicated. Again, now we're going to do an integration with respect to that vector, because what we're going to do is define a multivariate Gaussian prior on that vector. Okay? So what does a multivariate Gaussian prior look like? Well, just a little aside here. Multivariate Gaussians. So I think I have to do a new one, because remember last time it really slowed up when I... all right. It really slowed up when I drew too much on the same page, didn't it? Okay, so I'll just do a new one to prevent that happening. Okay, so multivariate Gaussian. So just an aside on that. What we have with a Gaussian density is something that we keep drawing. It looks like this, yeah? Now Gaussians have this odd property. It's odd because not many other distributions do it. That if you multiply... I meant to have some slides on this, but somehow I forgot. In fact, I do have some slides on this somewhere. If you had the Gaussian distribution over weights and heights, if you multiply weights by heights, so you've got a probability of the weights times the probability of the heights, then what actually happens is you get a spherical density. So you get, what I'm trying to show here is a plot of the contour, because it's now two-dimensional input. So think of this as a hill. So these are two sort of side bumps, and then what you do to get a joint distribution of independent Gaussians is you multiply them together like this. And if you do that, then you get something that looks like that, or if the variance of the weight is larger than the variance of the height, you get something that looks like that, or conversely, if the variance of the height is larger than the variance of the weight, you get something that looks like that. The way we define these things is as a covariance matrix, but these special cases, what happens is that covariance matrix is just diagonal, where you get a variance which is associated with the weight and a variance that's associated with the height. Okay? So in this case, for example, this contour is like a contour that I'm drawing would be like a contour 1 standard deviation. So it's like taking that point and circumscribing it, and this height and weight, so this sort of distance from the center of the Gaussian, so this is the mean of the Gaussian. The distance from the center of the Gaussian there is going to be sigma h. That's the standard deviation in that direction. And the difference, if we're looking at this narrow one here, that's going to be sigma W. Now what else can we do? Well, it turns out we can rotate this Gaussian. So we can perform a rotation on that space, and we could come up with something like that. And that's a correlated Gaussian covariance. And the right way of thinking about that is applying a rotation matrix. So a rotation matrix, who's done computer graphics? Okay, great. So you know about rotation matrices. This is a two-dimensional rotation matrix. It's just taking an ellipse like that and rotating it around. It's very easy to do, but the effect of having done it is to give us a Gaussian which has off-diagonal terms. So we'll call that still sigma w squared, we'll call that sigma h squared, and then here we have like a sigma wh, we have a sigma hw, which is exactly the same. Because we rotate this diagonal, and you basically, it's like, if you think of what the rotation does, it's like taking a point which is plotted here at sigma w, sigma h, and rotating it around. What the end result is that you start with a basis of that form and you end up with a new rotated basis. Still sigma w, so I've drawn that badly because that should still be sigma w and sigma h. But the basis is now located in a different position. And that's the basis of this new matrix. So it's like thinking, this rotation is like thinking, oh, I've got that. Basically, these are my primary axis of the Gaussian before it's rotated, and now these are my primary axis. And that direction here tells you the direction of correlation, where things are moving together. Now, I don't want you to fret about this too much. Hopefully we'll get more familiar with it. But a covariance matrix, which is how you express this stuff in a multivariate Gaussian, gives you, in this element here, the variance of the marginal, and here this gives you the covariance, how those things move together. So if this is a distribution over W and H, this is the whole matrix becomes the expectation of, well, this element here becomes the expectation of W times H minus the mean of W times the mean of H. So this is expectations in the way that I introduced them in the early lectures. So that's that element there. I wanted to put something else now. What was I going to put? The element here is W squared, the expectation of W squared minus expectation of W, which is the variance. But this term is showing how those things move together. So what it's saying is, in this case here, where its axis aligned, there is no covariance. They just move independently. They're independent. But when you rotate, you get these dependencies. And these are key. These are actually where all the interesting things happen. What will happen in the posterior for these multivariate regressions is that you'll find that you must have correlations between the gradient and the offset. Why is that so? Because if we think about this problem, this is our primary problem. This is what we're trying to solve. Someone's only given us one data point. If we say the offset is here, that's a possible offset. There's nothing wrong with that offset. But we then know that the gradient must be positive. Otherwise it won't go through that data point, or the gradient's likely to be positive. So if the offset is below that point, the gradient will be positive. However, if the offset was up here, so that's case 1, case 2, now the gradient must be negative. That's a correlation, or it's actually an anti-correlation. Because as we move the offset up, the gradient's gone down. So in order to represent that in a distribution, we actually have to have something like this. So now, let's get rid of h and w, and let's think this is going to be our posterior over c and n. And what's happening is, as c goes up, m goes down. And as c goes down, m goes up. So we need to be able to express that information, that correlation information. In fact, observing data just does that. It induces correlations all over these posteriors. So we start with a prior that is uncorrelated. We see some data, and it induces all these correlations because it constrains the sort of things that can happen. So, and if c is in the middle, obviously, then w is in the middle. So that could be exactly represented by a distribution like this. So we need this multivariate Gaussian form expressing these correlations. Now, another feature of this. So that's the form of our sigma. How many people have done eigenvalue decompositions? Anyone see? Yeah? This is an eigenvalue decomposition of the covariance matrix. They're going to come in again for principal component analysis. And for me, this is what I understand an eigenvalue decomposition as. So for me, whenever you tell me someone's doing an eigenvalue decomposition of a positive definite matrix, any positive definite matrix, I mean, I actually use this even if it's not positive definite. Because, I'll talk about positive definite for this in a moment. Any positive definite matrix has an associated Gaussian. And I'm drawing the ellipse. Okay, so to be clear of what's going on, there would be contours like this, and then the contours drift out as we go out here. Yeah, so it's like a hill, this probability distribution. Normalizes to 1 as before. So to me, an eigenvalue decomposition is just finding the principal axis, we can think of them, of that covariance matrix. It's finding the rotation that would turn that covariance back to something that was axis aligned. Yeah? Those are the eigenvectors, and they form the matrix R. These are the eigenvalues, and they give us sigma, well, sigma c and sigma m in this case, for the two-dimensional case. The length of those axes. So an eigenvalue decomposition, physically, I mean, I was taught them as a mechanical engineer, and they're used for natural frequencies of dynamical systems. And I never really had the intuition for what they meant. But now for me, they are physically, I think of them as giving me the axis on which a Gaussian's sitting. So the principal eigenvector gives me the dominant axis, the most important axis of highest variance. And if the principal eigenvector is pointing +1, +1 in that direction, it's not going to be +1, +1 because it's got to be normalized. Because the point about a rotation matrix is that that must be true. That's what defines a rotation matrix. That R transpose times R must equal the identity. So it's an orthonormal matrix, we call it. And the eigenvectors are also an orthonormal matrix if there's a symmetric matrix, if you're doing the eigendecomposition on a symmetric matrix. If it's a positive definite matrix, these eigenvectors are always positive as well. And that's important because you can't have negative variances. So the covariance matrix has to be positive definite. Why does it have to be? What does positive definite mean? Okay, so positive definite is the idea that this term, which is a quadratic form, doesn't matter what the value of t is, this term in here, let's ignore the minus, is always positive. Now this is important because it relates to the univariate case. In the univariate case where we're looking at a Gaussian, we've got, sorry, there should be -1. 1 over sigma squared t squared, like that. Variances are always positive. The square's enforcing that here. A negative variance makes no sense. You can't normalize a Gaussian with a negative variance. This is extending that concept to multivariate. So positive definite means that these eigenvalues that we start from all must be positive. The sigma squared W and the sigma squared H must be positive. But it extends it to the matrix that once we've done it's obvious, you can see the diagonal's positive if you've got a diagonalized matrix. That's fine. So that positive diagonals, that's always true of. This form, this quadratic form, can never be negative if this is a diagonal matrix with positive values. But it's less clear if I write down this matrix. It's less clear whether it's positive definite. In fact, I know that this matrix, but positive definite, this matrix is called positive semi-definite because it can have a value of 0. But if I were to make that 1.1 there, that matrix is not positive definite. Whereas this matrix is positive definite. Now, it's actually difficult for you to tell that. I happen to know that in this case. But that one could lead to, is a valid Gaussian covariance. That one is not a valid Gaussian covariance. The covariance must be positive definite or else the Gaussian is not normalizable. Okay? So final thing, the form of a multivariate Gaussian distribution, if it's k-dimensional, is this. So then we're going to be using this a lot, so you're going to get familiar with this. So we'll define it over T. T is a vector, mu is a vector. Sigma minus 1 is the inverse of the covariance. Now, let me write underneath. So I'm just, for comparison's sake, writing down what this would be in the univariate case. A lot of distributions don't extend elegantly to multivariate. The Gaussian does. And it's one reason why it's so useful and powerful. So you can see that this would reduce to that if we took the case where sigma was just a 1 by 1 matrix of the form sigma squared. In that case, so this lines here are the determinant. The determinant is actually the product of these, what we call eigenvalues. So, which is normally written, so the eigendecomposition of a positive definite matrix is of that form. The determinant, this is a diagonal matrix and this is the constrained, these are the rotation matrices. So U is giving us these principal axes, lambda is giving us these off-axis directions. The determinant of a matrix turns out to be equal to be the product of the diagonal of the eigenvalues. So in the independent case, that's what you get, just the product of the diagonal of the eigenvalues coming out of this determinant. Now remember that we've been looking at forms where we have sigma squared 2 pi sigma squared to the n over 2. Yeah, that's come up a lot. That's a multivariate Gaussian, which is a diagonal covariance. So it is a multivariate, but it's coming just from multiplying lots of independent Gaussians. It's just a very simple multivariate. And in the case where this is a diagonal covariance with sigma squared all along the diagonal, these two are equivalent. In the general case, where you've got these rotations going on, you need to be able to compute the determinant of a matrix. How difficult is it to compute the determinant of a matrix? Does anyone know how difficult it is? Anyone have any idea? Okay. How difficult is it to compute the determinant of a matrix? I'm just making a matrix that I know to be positive definite. Sorry, I've looked at the wrong thing. So that's a positive definite matrix. How difficult is it to compute the determinant? Ow, that was painful, wasn't it? This is why MATLAB and Python and these things are useful. So, how difficult is it to compute the eigenvalue decomposition? Not very difficult. Now, because I sampled in this case from a random Gaussian distribution, and then effectively here I computed its covariance, turns out that this is dominantly diagonal. So if we look at the covariance of x, you see there's very little off diagonal on it. So the eigenvalues point, and this one points negative, it could just as well point positive, yeah? Doesn't matter, it can be flipped around. So the eigenvalues are almost pointing in 1, 0, or minus 1, 0, and 0, 1. So they're axis aligned. If I define a covariance matrix, so...
Does that mean that there's very low correlation?
Yeah, there's no correlation pretty much. So here, this, I'm going to make massive correlation. So here's another covariance matrix. If we look at the eigenvalues of this, look at that. Square root of 2, square root of 2. They're almost axis aligned. I mean, just to prove that that's, well, square root of 2 divided by 2, that is, approximately. So very, very strongly correlated matrix because I made these off-diagonal elements large, yeah? Let's look at sigma. What else is worth showing there? So if we were to draw that, we would actually be drawing something very tight like that. It's interesting because it means that if you know, as you get closer, you start getting, this covariance matrix here isn't, there's another covariance matrix that isn't quite a valid Gaussian distribution. If you make a covariance matrix like this, of 1s, it's not actually positive definite, it's positive semi-definite. So it only has one eigenvalue. So you see this 2 here. It's only got one eigenvalue, the other one's 0. And the eigenvector associated with that eigenvalue is this one, 0.707, 0.707. It's exactly axis aligned. And what that's saying, the other one's 0, so it's saying this is so strongly correlated that there's no variance in one of those directions. So we can draw this covariance, the contours of it, it's just a straight line. Because it's saying there's 0 variance in that direction. That's one of the eigenvalues. And there's a variance of 2 in that direction, the way I've... there should be a variance of 1, shouldn't it? Yeah, variance of 1 in that direction. So basically that's saying that these two things are equal to each other. You can't quite sample from this Gaussian. So I've sampled from this Gaussian. You can always sample from a distribution, right? So here I'm sampling from this Gaussian distribution, and it's two-dimensional because it's in a two-dimensional space. Yeah? So I'm sampling from this Gaussian distribution. I'm asking for 2 values. I've given it the covariance that we've just been talking about, sigma, and the mean I've given is 0. And I've asked for 10 samples. What do you notice about those samples? Each one's exactly the same. because they're 100% correlated. So if we plot then you just get a bunch of line crosses along the line there, yeah? Now if we were to make that, so let's go to one of the other sigmas we used. So we can reduce the correlation now. So here I've reduced the correlation to 0.99. Let's do another sample. So change the sigma. Okay, look, they're close, but no cigar, as it were. Minus 0.11, minus 0.109, minus 0.118, minus 1.43. So if we now plot these, see they're correlated, but they're not exactly on the line. They've lost a little bit. There's a little bit of variance in that direction now. And we know how much that variance is if we do the eigendecomposition. There it is. So 0.01 in that direction and 1.99 in the other. Dominated by so they're going sort of, the variance there is 2, pretty much, and the variance there is 0.01. Yeah, that's what the eigendecomposition is telling me. So the variance, sorry, so the variance in this, so this is the eigendecomposition. This is the lambda. Sorry, I should have kept the notation consistent, shouldn't I? So when I wrote, so this is the eigendecomposition, and these are the eigenvectors. So this eigenvector associated with this eigenvalue, I don't know why MATLAB does this, but it always puts them backwards. So you often are interested in the principal one, and the principal one's typically the last one for some reason. So there's the eigenvalue, the larger one, and that's associated with this direction. And what that's saying is, we have to find the origin here. It's pointing in square root over 2, square root over 2, so that's directly up there, and it's saying the variance in that direction is 2, or 1.99. So the variance there is 1.99. So the standard deviation would be square root of 2, about 1.14. Now it just happens through randomness that it's put more down to this left quadrant than it has up to that right quadrant, but that's just because we've not sampled many. Let's sample a few more actually just to demonstrate that. If we sample very many, you'll really start to see the form of that. Oh, sorry, I should have gone more than 100. Yeah? So now there, and it's saying that the principal direction of variance is +1, +1. Let's try and get some axes on. I would love to be able to do this in Python. It would be so much cooler, but I'm just not as fluent in Python as I am in this. This is Octave, but which is a MATLAB. So you can see, look, that's the that's the x equals y line, which is what it's telling us is the direction of dominant correlation. This line going up here, and it's saying that the variance in that direction is 1.99. Now the interesting thing is the marginal variances of this thing are 1. So this is, if we look at sigma again, the marginal variance of each direction is just 1. So the variance, if you were to just project this down, so if you were to look at a one-dimensional distribution, so let's do that. Let's histogram like that. So just histogram those values in one dimension. Oh, golly golly, look at that. The standard deviation is 1. It's kind of misleading though, because you look at that, you think, oh, this is quite a noisy system, don't you? Look at that. And then look at the other one. So let's just plot histograms in those two directions, 2 dimensions. There's our data, all histogrammed. Now we know everything about our data that we need to know. Until you suddenly realize, well, actually, that's really misleading about what's actually going on in the data. What looks like a highly uncertain system is really strongly correlated. And what these diagonal things say is the marginal variance is a 1. The marginal variance is 1, which you can see here. That's the standard deviation there. So that's when you project these guys down onto the 2 axes. But when you look on this axis and you do the eigen decomposition, what you see is, the dominant direction is x equals y, pretty much, and the variance in that direction is actually 2. Close to 2, not quite 2. Does that make sense? You're getting a feeling for these sort of things, what they can do? So, you know, in the example we're looking at, okay, let's go the other way. We can actually create a sigma which is anti-correlated. Okay, so if we get a sigma that's anti-correlated, we'll look at the eigen decomposition. Now we see minus minus and minus is an off-diagonal thing. So the direction of largest variance is not any more positive positive, it's minus. So it's going, well, let's plot it. Going in the opposite direction. X equals minus y. So you get really familiar with these. I mean, it's simple, but it's really important. And as things go high dimension, principal component analysis, which is what we're going to look at, is exactly what we've just been doing it. But we'll look at the probabilistic model behind it. So principal component analysis, which we'll look at next week, is just finding those directions. It's doing the eigen decomposition on the covariance matrix. So maybe I should have given more of this material, and I'm running out of time to give this week. So I'll probably end up having to shift material between the weeks. But it's important to not be afraid of a multivariate Gaussian. It's not a big bad wolf. It's just a setup where you're expressing in multiple dimensions and you can express correlations. And all you express is correlations. There are other statistics that it just assumes doesn't exist. Third order, fourth order. It's a very nice, elegant, multivariate distribution. Okay. So I'm going to run out of time on this stuff, but it doesn't matter because some of that material I've just been talking about also could have been told next week. So here, these are multivariate Gaussians. They are multivariate Gaussians secretly, but they're very, very simple ones. They're ones which are axis aligned. So look, the independence, this sum up here is a giveaway of independence. I've written this as an inner product, but that just means it's a sum. It just means it's a sum of wi squared. Yeah? So that is also a sum over the dimensions of w. I've just written it as an inner product. It's always equivalent, so just to be clear on that. What I'm trying to tell you is that W transpose W is equal to, if we take the elements of W, is equal to that. Where there's P, where W's P-dimensional. So that's another independent Gaussian. It's multivariate, but uninteresting multivariate. But now what's cool is you take those two uninteresting multivariate systems and you multiply them together, and what you get out is a correlated system, where the correlations are induced by the data. So let's do that. And I think that's all we'll have time for. We'll have to do basis functions next time. It really gets exciting with basis functions once we start, you know. I know you're already on the edge of your seats to see what we'll do next, but you wait till we introduce basis functions. Okay, so see if I can remember those likelihoods. So this is data given the matrix of input data. We're going to use that matrix form. And, sorry, not square root there. We have our old friend. So this is coming about by the IID assumption. That's why it leads to an independent Gaussian. Okay, so I'm using this little notation here. This is my MATLAB notation. to indicate that that's the ith row from X. But we could equally write xi. I always mean that the ith data point. So I would just put that colon notation to say all the elements from the ith row. We use that in Python as well to extract. So it's a Python MATLAB type notation, just to say take the ith row from this matrix. But we can think of that as just the ith data point, the input. P of W. I've missed the factor of 2 and the noise. No one spotted that, sorry. Okay. Now this is very similar to the optimization we had to do for maximum likelihood in this system, that we're going to have to multiply out this guy again, and we're going to multiply it out in the same way. So although I guess we're introducing more complex concepts, we're just doing the same thing again and again. So as long as you get familiar with these sort of operations, you know, you should be all right. So we'll multiply. Sorry. P, sorry, yes. P is just the dimension of the system. So, yeah. So the matrix X is sort of n rows. Well, this is a notation meaning the matrix X is n rows and p columns. So meaning there are p different inputs. So if it were an image with 8 by 8 pixels, p would be 64. Okay, so I should really switch off Skype, shouldn't I, before I... The great thing is it's being recorded for all prosperity as well. So now we've done this multiplication out before, so I won't go through it as quickly, as slowly.
PW multiplied by
yeah.
PT.
Yeah, sorry, yeah, just to clarify, we're doing the same thing we did in the univariate case. We're multiplying these two together, and to do that, we're just multiplying out the exponents and adding them together. So I'm just collecting the terms together. We did the multiplying out of this guy on Tuesday for when we did maximum likelihood. Now, I'm going to do... So remember this trick of writing that one the other way around, yeah? Remember that from last time? Which means we can bring that sum in and form a matrix there. Okay? So that's just the same trick applied again. We have a limited number of tricks in the bucket. Sorry, I'm missing the factor 2 there. And that should be a minus. Sorry. And then we've got final term is I equals 1 to n of ti xi transpose w. Now we need the term from P of W, so that's minus 2 alpha W transpose W. Okay, so what do we do next? We want to find the Gaussian form. So can anyone tell me what we need to do now? Exactly the same we did in the univariate. Yeah, extract precision matrix or covariance matrix and extract the mean. So we need to return this. What we want to do is recover this in a form that looks like this. I'm going to index mu by W to indicate that it's the posterior. That's what we want to see. Why do we want to see that? Because That's the form of the Gaussian in the exponent. So this is just a quadratic form. That's a vector, that's a matrix, that's a vector. Vector transpose matrix vector, quadratic form. Just the multivariate version of a quadratic. So now what we have to do is the multivariate version of completing the square. So, the covariance first. So for the covariance, we need to find all terms which are quadratic in W. Now, we've lost the ability to look for 2's because quadratic terms don't appear with 2's anymore. They appear as W transpose matrix W. Now, there's no matrix there, but there is, because secretly there's the identity matrix there. So the way we have to extract that, so if we want to combine these two terms here together, I'll write that in red to show that we're just doing those two. What we want to do, I can bring that sum in, but we want to have a W starting. Now I need this matrix to be the sum of xi. This is the same matrix we extracted before for I don't want to write the W yet because that's part of it. I now have to add this term on. And to add this term on, I've got the factor of half outside, so that's okay. But I have to look at this. I have to pretend, I have to see the identity matrix inside there. Alpha to the minus 1 times I. Like that. So think of multiplying that out now. If you bring this in here, W transpose times that matrix times W, that leads to that term. W transpose times alpha minus 1I times W leads to that term. Okay, so that's the sort of thing we want. So what is this little baby in here? That is the inverse covariance matrix. Precision matrix. So we've already got our covariance matrix. What's happened? We've got a bunch of off-diagonal terms coming from the data, yeah? In fact, we saw last time, I told you last time that I like to write that in this form. This x here, this x transpose x, is actually a sample-based approximation, not to the covariance matrix, but to the second moment of your data set. In fact, it's what I used earlier to generate a covariance matrix randomly. So we have a term that's inducing correlation, and then we have this spherical term. I think of this as a spherical term. Why do I call that a spherical term? Because if we would just look at that, a covariance based on that guy, then what we would find is it was a spherical Gaussian. So if I talk about spherical terms, what I really mean is, that this would lead to a spherical Gaussian. Yeah? Because it's in every dimension, it's coming from our prior, which was a spherical Gaussian. And then this term's going to introduce correlation. Yeah, that's right. So that was like our prior, and that term's coming from there. Well, this, of course, this is all being inverted. So actually, it's not just a sum of those two type of terms, because it's being inverted as well. So the inversion actually requires a different formula, which we're going to come across later if you want to see what the spherical term is. But it does turn out that that appears as a spherical term in the inversion. Okay, so we've got our sigma W. So we're now left to find our mu. What do we look for mu? Well, let's have a little look-see in this guy. And what if we multiply out to find the linear term, what it's going to be, the linear term is going to be of the form 2 sigma W sorry, 2 times, W transpose sigma W mu W. Why do I write 2? Yeah, I should pause there. I was going to go through that too quickly. But let me pause there a bit. And we're running out of time a bit. So maybe I'll have to review this on Tuesday. But let's just spend a bit of time multiplying this out. So what do we get if we multiply this out? That term times that times that. It's just like a regular quadratic form, but with matrices. And we get a minus that term times that times that. Then we get a, from the other side, we get a that term times that times, sorry, we get that term times that times that, but then we also get a that term times that times that. There's always 4 terms, like in every quadratic, but this one is that way around. Now normally, in a normal quadratic, you can immediately combine these 2 terms, the 2 terms that arise there, into one. Here it's a little bit more subtle, which is the point I wanted to bring out here. And then in final you get that term times that times that. Okay, what goes wrong? Well, is that term equal to that term? The answer is it depends. What it depends on is, because it's a multiplication across 3 things, so it depends on whether this is symmetric or not. And it is symmetric, so they do equal each other. So if I were to write, this is a scalar, right? So you can, if you transpose this whole thing, it's a scalar, so a transposition of it is equal to itself. So it's a scalar. If I transpose what's 2 transposed, it's equal to 2, right? It's not a matrix, it's a scalar. Now, if you transpose a matrix multiplication, you have to reverse the order of the matrix multiplication and transpose everything inside the order. So that is equal to W transpose sigma W inverted transposed times mu W, because mu W transposed is mu W. So if sigma W inverted transposed is equal to sigma W inverted, then these 2 things are equal to each other. And indeed it is, because we defined it to be a covariance matrix, and that covariance matrix must be symmetric. So basically these 2 are equal to each other for this quadratic form, so we can rewrite that as W transpose sigma W minus 1, W minus 2, and we can choose whichever way around we like. I like to choose the way around that keeps the variable I'm interested in as a vector instead of a vector transposed, but it really doesn't matter. Sorry, that should be mu. Yeah, so that's the multiplying out of that quadratic form. So now we need to match that linear term to the linear term we're seeing here. So in other words, we need to set, and having said I write it that way round, I actually prefer now to write it the other way around. W transpose sigma W minus 1 mu W has to be written as equal to this thing here, which is, I'm going to write as 1 over sigma squared W transpose. I'm transposing what's inside that thing as well. Transposing all the time, sorry. If I were organized, I wouldn't be doing that. Okay? And the reason I've done all that transposing, I should have just kept them both the same way around. The reason I did that transposing was to make it clear that the W on each side disappears. You can get rid of that, and then you need to multiply by sigma on both sides. So you get mu W, multiply both sides by sigma W. The sigma W on this side disappears, and you get 1 over sigma squared, sigma W, sum for I equals 1 to n, Ti xi. Okay? So that's the solution for mu. Now the final thing I want to note, we're overrunning slightly, but just since we're there, so let's write down what sigma W was, which was x transpose x, is it divided by sigma squared, isn't it? Yeah. Sigma minus 2, x transpose x, plus alpha minus 1i, minus 1. And if we substitute that in for mu W, we get 1 over sigma squared, x transpose x, times sigma to the minus 2, plus alpha minus 1i, minus 1. This guy, I'm going to do the same thing I did after maximum likelihood. I'm going to rewrite him as x transpose t. I like to see them in, it means I don't have to write all these sigmas. If you don't see why that is the case, I mean, it's the definition of matrix multiplication, and the definition I've given x is why that is the case. Please make sure you understand why you can do that. Write this inner product. It's not an inner product, it's a multiplier of each vector. It's a sum of a bunch of vectors, weighted sum of vectors in this matrix form. Now, alakazam, as they say, if I bring that in, oh, isn't it wonderful? Just like before, I get a very similar effect that this looks extremely like the maximum likelihood solution. Yeah? Okay, we've got to finish up there because I think someone's outside. I thought we didn't have anyone following us. Okay? So we'll take another look at that at the beginning of next time, because there's more material to do on that. And then we'll start, I spent too long, well, I didn't spend too long, I spent the right amount of time introducing multivariate Gaussians, but more time than I expected.
Are you going to Citroën today?
Yeah, I've got to go up to